Hello, in this video we will talk about ordinary least squares estimators in linear regression. So we know in linear regression or very simple type of linear regression is called two variables linear regression because there is only a dependent variable y and one explanatory variable x in the equation. And this equation called two-variable PRF. So PRF means population regression function. So this means we know the variables between x and y, and there exists some relationship between these two. And we want to estimate the relationship or the parameter beta 1 and beta 2 from this equation. So here the UI means disturbance. So disturbance means we know xi related to y, but we cannot include all the x variables in the equation because of we have no data or because of they are very simple, very little effect than the main variable. So we include all these factors in disturbance, and this is called the UI. So this is the population regression function or the population regression line. But we do not know the real value of beta 1 and beta 2. So beta 1 is the intercept and beta 2 is the slope. So what we can do is to estimate these two parameters from the sample. So this is called a sample regression function. yi equals beta 1 hat plus beta 2 hat times xi plus ui hat. So here we use a hat because we want to, these two values are estimated from the sample. So different sample will get different parameters, beta 1 and beta 2. So this is the estimation. So what we can do is to estimate this one to represent the population regression function. And here ui hat is called error or the residue. And here the yi hat is called conditional mean of yi. So here the conditional, what is the conditional mean? So this means for given xi value, we have a yi hat. Because different value of xi can have different value of yi in the sample, right? For example, we see next page. There is an example from income is x and y is expenditure. So the higher income usually will get higher expenditure, right? For the different families. But if you look at, for example, income is 100, we have sample, but they are not necessarily the same on the one point. So what we can do is only estimate this one is the sample regression function line. So this straight line means for each point on this line means for given x we have and conditional mean value of y. So we can only estimate the conditional mean of y from given xi. But actually there are very many samples for each xi value. There are the group of different yi on this xi value, right? So this picture shows like for each given xi for the y value there is a distribution like. So here this points like the mean value of this distribution, but this distribution is not for all the y value, it's only for the given xi's y value, right? So next we have to think about how to estimate these two parameters beta 1 hat and beta 2 hat, and we have to use some criteria. So but one criteria is called ordinary least squares. So what does this mean? If we look at this residue actually is the actual y value. So we observed this y value from the sample minus the beta 1 hat minus the beta 2 hat times xi. So these two parts, the summation is actually the conditional mean of yi given xi on the previous page's line, right? So we use yi minus this part, get the residue. And we want to make this residue as small as possible. This is the main criteria. So if we make this as small as possible, then this line will be as close as to the actual y, right? So if we look at this figure again, this is the residue because this is the actual y for the given xi. Of course, there are many, not only one, right? The group of yi given xi. For each yi, we have one residue. So ui hat, and same as this one, similar to this one, they are all residues. And you can see the residue can be positive, which means the actual y over this line, or negative if the actual real y lower than this estimated conditional mean of y given xi, right? So if we just simply sum this residue together, so the values can be washed away, no matter even there are very large difference between y and this SRF line, but the residual summation will be washed away, disappear. So this is not ideal case. So we have to think about the absolute value of the residue. So there comes the least squares. So we just sum together the squares of this residue together. So this is the yi minus beta I hat minus beta 2 hat times xi. Of course, these two parameters is what we want to estimate. Use this formation. So this is the residue, take a square, then sum together. Very easy, right? So this is all the sample. We take all the sample, not only one y value given xi. We take all the samples value, then take it together. This is called least square summation. So we make these items as small as possible. So this is the best case what we can do, right? We can make this as small as possible, then which means the residue will be small, and the estimated line will be close to the real y value. So if we make a differentiation partially with respect to these parameters, beta 1 and beta 2 hat, so we can get these two elements, right? So this partial differentiation with respect to beta 1 hat will get this item. This item actually is the 2 times sigma residue, right? And the sum of squares of the residue differentiation with respect to beta 2 hat will get this form. This form actually is the residue, each residue hat times each xi, then take summation. So because we want to make this residual summation together as small as possible, so one requirement is we have to make these two equations, these two items to 0. This is optimization theory, right? So if we make these equations 0, we can get these two equations. So sigma yi equals n beta 1 hat plus beta 2 hat times sigma xi. And sigma yi times xi equals beta 1 hat then times summation of x then times beta 2 times summation of the xi squared. And these two equations called the normal equations because in the two variable linear regression, there are only one explanatory variable x in the equation. So we have two such simultaneous equations called normal equations. In a more complicated linear regression with more than one explanatory variables in the equation, so there are more than two simultaneous equations called normal equations, right? Then after some manipulations, so we can get beta 2 hat equals sigma. Here we use lowercase alphabet xi times yi divided by sigma xi times xi squared. So lowercase means the difference between x and its mean value. So we have all the x value. For example, income, we have 60, 80, 100 to 120. Then sum all these observations x value together, then divided by sample size, so we get this mean value of x. So each xi minus its mean value, this is the difference if we use lowercase alphabet. And similarly, yi lowercase is each observed y value in the sample minus the mean value of y. So similar in these elements, so here is the sum of the square of the difference between xi and its mean value. So beta 2 hat can be expressed as this division. So after we have got the beta I hat estimation, then beta 1 hat will be looked at easier. So here is only y mean value minus beta 2 hat times x mean value. So note that here is not lowercase, is the uppercase, so which means this is the observed value, not the difference. So here we use the difference, lowercase value. So this is two parameters called ordinary least squares estimators. And if we say we have different samples, we make experiments, for example, 100 times. So each time we get the beta 1 hat and the beta 2 hat not the same. But this is the best what we can do, because we use the criteria for minimization of the sum of residual square. Thanks for watching.